Welcome to AI Research Weekly, the podcast that keeps you at the bleeding edge of artificial intelligence. I'm Nova.
And I'm Onyx. This week, we're diving deep into the rapidly evolving world of agentic AI, from novel attack vectors that exploit contextual reasoning to advanced frameworks for autonomous skill acquisition and efficient context management. It's a field moving incredibly fast, and the research this week truly underscores both its promise and its peril. Absolutely, Onyx. The sheer volume of papers focusing on agentic systems right now is staggering. Our intelligence systems processed 500 new papers, identifying over 1,300 concepts, with a significant chunk orbiting around agentic AI, context engineering, and especially the security and trustworthiness of these autonomous systems. It really feels like we're moving past the can it be done phase and squarely into the how do we do it safely and effectively at scale era. Precisely. That shift is evident in the first paper we want to highlight. Mind the Web, the Security of Web Use Agents. This work from a team at, interestingly, a cross-institution collaboration, including some emerging security researchers, introduces a truly insidious attack vector called the task-aligned injection attack.
Task-aligned injection. That sounds far more sophisticated than your typical prompt injection. What's the core innovation here?
It absolutely is. The key contribution is showing how malicious web content can be framed as helpful task guidance to exploit an LLM's contextual reasoning limitations, causing the agent to deviate from its original goal. Unlike a direct adversarial prompt, this attack leverages the agent's expected behavior and context understanding against itself. Essentially, the malicious content looks innocuous or even beneficial within the agent's operational frame, leading it to self-sabotage its assigned task.
So, it's not just injecting bad instructions, it's camouflaging them as good ones. That's a big deal for agents designed to browse and interact with the open web. What kind of success rates are we talking about?
They developed an automated 3-stage pipeline to generate these task-aligned injections, and it achieved an attack success rate of over 80% against 5 popular web use agents, including OpenAI Operator, Browser Use, and Perplexity Comet. What's more concerning is the attack's strong transferability. It worked across unseen payloads, diverse web environments, and even different underlying LLMs. Even agents with built-in safety mechanisms were vulnerable. This highlights a critical, previously unexplored attack surface due to web use agents' extensive browser privileges.
An 80% success rate on 5 different agents, even with safety mechanisms. That's alarming. It implies our current agent safety paradigms are fundamentally missing something when it comes to web interaction. It's not just about guarding against explicit refusal, but about subtle manipulation. What are the proposed mitigations?
The authors suggest several strategies, primarily focusing on robust oversight mechanisms, stricter execution constraints, and more sophisticated task-aware reasoning techniques. The challenge, of course, is that these often introduce trade-offs with agent autonomy and efficiency. It really pushes us to consider how to build agents that are both powerful and inherently skeptical of external context, especially when that context is dynamically loaded from potentially untrusted sources.
Right. It brings to mind that fundamental tension between agentic autonomy and control. We want agents to be smart and adapt, but that adaptability is precisely what can be exploited. This paper is a wake-up call for anyone building or deploying web-enabled LLM agents.
Agreed. Now, shifting from security challenges to advancements in agent capabilities, we have another fascinating paper. EvoDS, Self-Evolving Autonomous Data Science Agent with Skill Learning and Context Management.
EvoDS, self-evolving. That sounds ambitious. What exactly makes it self-evolving, and how does it tackle skill learning and context management, which are perennial challenges for long-running agents?
The core innovation of EvoDS lies in 2 key strategies: autonomous skill acquisition and adaptive context compression, ACC. ASA allows the agent to synthesize, validate, and reuse executable skills on the fly, essentially learning and improving its toolset. ACC treats context management as a learned control problem, moving beyond static context windows or simple summarization.
So it's not just using predefined tools, it's actively creating and refining its own operational knowledge. And learning to manage context dynamically, that's huge for complex data science workflows, which are inherently multi-step and often involve massive amounts of intermediate information.
Exactly. The training scheme for EvoDS is a two-stage multi-agent process. It starts with collecting trajectories from a teacher model for supervised fine-tuning, then moves to online reinforcement learning to jointly optimize task performance, skill acquisition, and context management. The hierarchical design is theoretically proven to reduce tool selection error, which is a common failure point for agents. Their optimization objective also aligns with an information bottleneck principle, ensuring efficient context use.
That's a really elegant approach. Connecting context management to an information bottleneck principle makes a lot of sense, pushing the agent to retain only the most salient information. What kind of empirical gains did they see?
Empirically, EvoDS outperforms state-of-the-art open-source data science agents by an average of 28.9% across 4 diverse benchmarks. This isn't just a marginal improvement, it's a significant leap in capability. Crucially, it also effectively eliminates out-of-token failures, a major pain point for developers using agents on complex tasks. It's addressing those fundamental limitations of static action sets and the lack of principled long-horizon context management.
28.9% average improvement and no out-of-token failures? That's compelling. It points towards a future where agents can handle more complex, multi-stage data science tasks with significantly higher reliability and less human intervention. The explicit learning of context management, rather than just relying on fixed-size windows, really opens up possibilities.
It really does. It's a move towards truly robust and adaptable agentic systems, especially for domains like data science, where tasks are often ill-defined and require iterative exploration. It demonstrates how embedding deeper learning within the agent's operational loop can lead to dramatic improvements.
Moving on, let's switch gears slightly to a fascinating architectural innovation in medical imaging. We're talking about knowledge-guided brain tumor segmentation via synchronized visual semantic topological prior fusion. Onyx, this sounds like it's addressing a very specific high-stakes problem.
It certainly is, Nova. The key contribution here is the Synchronized Trimodal Prior Fusion, or STPF, framework. This isn't just another deep learning model, it explicitly integrates medical domain knowledge, pathology-driven differential features, unsupervised semantic descriptions, and geometric constraints into the segmentation process. This goes beyond purely data-driven methods, which often struggle with the nuances and variabilities in complex medical images.
So it's about injecting expert knowledge right into the architecture rather than just hoping the model learns it from data alone. In medical imaging, where data can be sparse or difficult to annotate, that's incredibly valuable. What kind of performance uplift did they achieve?
On the BRATS 2020 dataset, which is a standard benchmark for brain tumor segmentation, STPF achieved a mean dice coefficient of 0.868. This outperformed the best baseline by 2.6 percentage points, which translates to a 3.09% relative improvement. In medical imaging, where precision is paramount, a 3% relative improvement can be clinically significant.
A 0.868 dice coefficient is strong, and a 3% relative improvement for segmentation is notable, especially in a challenging domain like brain tumors with ambiguous boundaries. What did their ablation studies reveal about the knowledge-guided components?
The ablation studies confirmed the critical role of those domain priors. Removing the topological priors led to a performance degradation of 2.8%, and removing semantic priors caused a 3.5% drop. This quantitatively validates the hypothesis that explicit integration of medical domain knowledge significantly enhances segmentation accuracy, particularly in those ambiguous boundary regions where purely visual cues might be insufficient. The framework also showed high stability with very low coefficients of variation, between 0.23% and 0.33% across 5-fold cross-validation, indicating robust generalization.
That stability is just as important as the accuracy in clinical settings. This approach really emphasizes the continued value of domain expertise in AI system design, especially in high-stakes applications. It's not just about bigger models or more data, but smarter integration of what we already know.
Absolutely. It's a clear example of how methodological innovation, rather than brute force, can lead to substantial gains and improve clinical deployment potential.
And speaking of deploying AI systems, especially complex multi-model agentic ones, understanding their performance characteristics and bottlenecks is critical. This brings us to the paper. Characterization of multi-model agentic AI systems on general tasks via trace-driven simulation. This sounds like it gets under the hood of agent orchestration.
It really does, Nova. This paper provides a crucial systems-level perspective on the next generation of agentic AI. Their key contribution is a novel, token-level trace dataset called Gaia Trace, which captures the full reasoning tokens, task-level structures, and activities of every major participating LLM for two state-of-the-art agentic systems, MyroThinker and Abel, running the Gaia benchmark. This level of granularity is unprecedented and reveals far more diverse agent behaviors than previously thought.
So it's a deep dive into the actual runtime behavior of these complex systems. That's invaluable for optimizing them. What did this trace data reveal about common assumptions in LLM system design?
It challenges several assumptions. For instance, they found that popular SLA metrics like tail time to first token, TTFT, or time per output token, TPOT, are often misaligned with agentic AI. Designs that worsen these per-query metrics can actually improve overall per-task latency. This suggests that prior optimization strategies, often focused on single-query LLM serving, might not be optimal for agentic workflows.
That's a critical insight. We've been optimizing for individual LLM calls, but an agent's success is about completing a task, which involves many calls. So an approach that might slow down one API call could accelerate the overall task if it helps the agent plan better or avoid recomputation. What other bottlenecks did they identify?
They found that the dominant system bottleneck in agentic AI shifts dynamically with task arrival rate. This makes static hardware provisioning brittle and necessitates dynamic reconfiguration for optimal GPU allocation across varying loads. Essentially, what's efficient at low load might be a disaster at high load, and vice versa.
That points to a need for far more adaptive resource schedulers, likely AI-driven themselves, to keep these agentic platforms running efficiently. Did they identify any particularly effective optimization techniques?
Yes, they found that prefix caching significantly impacts end-to-end task latency, improving it by 1.67 to 3.82 times in their study. This is substantially larger than what's typically reported for single LLM calls, sometimes over an order of magnitude higher. However, they also noted that these benefits are uneven across components and can sometimes even degrade TTFT for specific subtasks, highlighting the complexity of optimization in multi-model agentic environments. The paper really motivates a deeper study into the unique system characteristics of multi-agent, multi-model, multi-tool systems.
A 1.67 to 3.82 times speedup from prefix caching is huge for real-world deployment. But the caveat about uneven benefits underscores that optimizing these systems is a whole new beast. It's not just scaling up, it's about smart, adaptive orchestration at every layer.
Exactly. It's a foundational piece for understanding and building the robust, scalable infrastructure that agentic AI demands.
Fascinating stuff this week, Onyx. We've seen a clear push towards building more intelligent autonomous agents. But equally important, the research is exposing the critical need for robustness, security, and smart system-level design.
Indeed. The convergence of agentic AI and context engineering as accelerating concepts in our intelligence brief really encapsulates this. We're moving towards not just building smart agents, but building agents that can reliably manage complex, dynamic interactions with their environment and with humans.
And doing so securely, as we saw with those task-aligned injection attacks. It's a constant arms race.
It is. And on that note, let's quickly touch on our Industry Watchdrotch segment for this week. The most significant industry buzz is definitely around the continuous deployment and refinement of agentic capabilities within enterprise platforms. We're seeing a lot of chatter about companies like Saluka Agentic AI Research Team, who are actively publishing and developing, signaling increased investment in this space. They're exploring how multi-agent systems can operationalize lean startup cycles, significantly reducing time to validated learning.
That connects directly to the EvoDS paper we discussed, right? The idea of agents not just assisting, but driving complex iterative processes and doing it faster than human-led cycles. It speaks to a very specific business application.
Exactly. And beyond that, the ongoing relevance of retrieval augmented generation, or RAG, continues to be a hot topic. While established in research, its commercial implementations are becoming increasingly sophisticated. Many new product announcements emphasize RAG's ability to ground LLM responses in proprietary data, enhancing accuracy and reducing hallucinations, which is crucial for enterprise adoption. It's no longer just a feature. It's a foundational component being optimized for scalability and latency, much like the systems-level insights we saw from the Gaia Trace paper.
So we're seeing research on agent security, self-evolving capabilities, and system optimization directly mirrored in industry's push for deployable, robust, and trustworthy AI solutions. It's a clear signal that the research frontier is rapidly translating into practical applications.
Absolutely. The compliance-first agentic platforms for healthcare, for example, which also surfaced this week, are another strong indicator that regulated industries are serious about adopting AI, but only with robust architectural guarantees for auditability and privacy, often leveraging federated learning and differential privacy. This shows an explicit move from ad hoc AI tools to governed, ROI-focused platforms.
That makes a lot of sense. The stakes are too high in those sectors to compromise on trust and verifiability. This week really highlights that as AI systems become more autonomous and integrated, the focus must broaden from raw capability to resilience, accountability, and ethical deployment.
My thoughts exactly, Nova. For anyone building in this space, keeping an eye on these converging themes, agent trustworthiness, self-improvement, and efficient system orchestration, is paramount.
That's all for this week's AI Research Weekly. Join us next time as we unpack the latest advancements and debates shaping the future of AI.
Until then, keep pushing the boundaries.